UV visible, IR, NMR, these all are spectroscopic method. Now, what is spectroscopy? It involves matter and it involves electromagnetic radiation. So, electromagnetic radiation consisting of self-sustaining, oscillating electric and magnetic fields are right angles to each other and to the direction of propagation. It does not require support medium and travels through empty space at speed of light. This is the definition of electromagnetic radiation with respect to what they consist of. Okay. Then there is alternate definition. Electromagnetic radiation is a form of energy emitted or absorbed by charged particles which exhibit wave-like behavior as it travels through the space. It propagates as wave motion at velocity of c is equal to 3 into 10 raised to 8 meter per second. So this is velocity of light, and light, as we know, is also form of electromagnetic radiation. So this is the definition of electromagnetic radiation. Coming to the next part, what is spectroscopy? Now we saw what is EMR. So this is spectrum plus copies. When a beam of light is allowed to pass through a prism or grating, it will disperse into 7 colors from red to violet, and set colors or bands produced from it produced is called as spectrum. So this is called as spectrum. Observing this spectrum, examining this spectrum is nothing but scopies. So examination of this spectrum is called as spectroscopy. Now this is the simplest possible definition. Just observing the spectra is spectroscopy. Now there are alternate definitions which are more useful. Spectroscopy is the branch of science dealt with study of interaction of electromagnetic radiation with matter. Now when electromagnetic radiation interacts with matter, both EMR and matter are subjected to some change. Like you must have seen that when you keep any food in a microwave oven, the food gets heated. So there is change in state of matter. Its temperature increases. And similarly, when electromagnetic radiation of, say, light passes through a colored glass, okay, when it passes through colored glass, its color changes. Originally, suppose if it is white, it acquires the color of the filter, the color of the glass, red, yellow, whatever may be the color, glass color may be. So there is change in some property of electromagnetic radiation. So both of them, when interact, electromagnetic radiation and matter, when they interact, they bring about some change in each other. The study of this change, study of this interaction is called as spectroscopy. So this definition is more useful to us than the previous definition. Now, so the spectroscopy means examination of the spectra. From the type of radiation which is absorbed, we can get the idea about nature, type of the compound, and from the amount of radiation which is absorbed, we can get idea about the concentration or amount of the substance. So what we are doing here? We are doing here analysis, chemical analysis we are performing. So the spectroscopy is used for qualitative and quantitative analysis. Now there are some properties related to electromagnetic radiation we need to study. We have seen what is spectroscopy. We know light is a form of electromagnetic radiation. We are going to see certain definition. First definition is wavelength. Now, any OCPN can answer what is the perfect definition of wavelength. Adnan, can you please answer? Can you tell what is wavelength?
Sir, distance between two peaks.
Distance between two peaks. Okay, that is not wrong answer. I will improve the answer. It is the distance between two consecutive points on the wave which are in the same phase of vibration. It is more appropriate definition of wavelength. Distance between two crests or distance between two successive trough. Yes, that is not wrong answer, but we need to talk about in terms of phase of vibration. Okay. Okay, Anjali Rai, can you answer what is amplitude? Okay, it is the maximum distance traveled by the wave particle from its mean position. Amplitude, the vertical distance from the midline of waves to the top of the peak or the bottom of the trough. That is called as the amplitude. Frequency, number of waves that passes through a particular point in 1 unit, 1 second, is called as frequency. So these are all the known frequencies, range of frequencies, and you can say there are different classification like radio waves, microwaves, infrared, visible, UV, X-ray, gamma ray. So it is all listed over here. You'll observe that very small part of these wavelengths is visible to eye, human eye I should say, and most of the other wavelengths are not visible to human eye. So these are the common spectroscopic method based on those electromagnetic radiations we saw in previous slide. We just go through this table. The first column talks about type of spectroscopy. Second column talks about usual wavelength range. Next column talks about wave number. Last column, type of quantum transition that takes place within the molecule or atom or ion. So first is very center to the atom, nuclear. Second type like X-ray, absorption, emission, fluorescence, diffraction, they may involve the inner electrons, not valence electrons, the inner electrons. Like that you go through the points. Okay, then there is something called as atomic spectra and molecular spectra. If it is atomic spectra, you will get a line spectra. This is emission spectra. So this is emission spectra, emission by atom. The line spectra are emitted from hot monoatomic gases. The atoms are not linked to each other in any way. Can anybody give me example of these hot monoatomic gases? Anybody? Shubham is saying NO. Whether he's saying no, he cannot answer, or he's saying okay, helium is right answer. In NO, there is nitrogen triple bond oxygen. So Shubham, that cannot be atomic gas. It is molecular gas. So helium, xenon, argon, all the noble gases and gases like sodium vapor lamps and all that, those gases can be considered. Now second spectra, if you'll observe, it is also emission spectra and you have some bands in that instead of lines. So that is emitted by molecules. So these are emitted by gas, but when sufficient energy is provided to these molecules in the gaseous form. Okay. Now then next is continuous spectra. The continuous spectra is generally emitted from hot solid. When we talk about solid, the atoms are compactly arranged and the intensity or wavelength distribution depending on the temperature of the solid. Okay, so that is the continuous spectra. Absorption spectra is exactly opposite that of emission spectra. If you talk about, if you think about absorption spectra of atoms, so you will find some lines are missing. And if it is a molecular spectra, you will observe that some bands are missing. Okay, you will observe that some bands are missing. Okay, so that is absorption spectra. Now, coming to the next concept, absorbance and transmittance. Observe this animated diagram here. See what is happening. there is a sample whose thickness, or there is a medium whose thickness is B, breadth B. There is electromagnetic radiation falling here who has got power or intensity P0. After passing through the medium, its intensity or power becomes P. So something was absorbed by the sample. Okay, remember these P0 and P. So this diagram, which is animated, shows a beam of monochromatic radiation of radiant power or radiant intensity P0. In some books, it is also referred as I0. Now that electromagnetic radiation is directed at the sample solution, directed at the sample. Absorption P, absorption of the sum of the intensity, sum of the power takes place by the sample, and the beam of radiation leaving the sample now has radiant power P. The amount of radiation absorbed may be measured in many ways. First is transmittance, indicated by T. The formula is P upon P0. That is intensity transmitted per intensity incident. Okay. Now there is percent transmittance. It is indicated by percent T, and it is 100 multiplied by T. That is 100 multiplied by P divided by P0. Okay. Now transmittance and percent transmittance, they are related ways of expressing how much power was absorbed by the sample. That way, A is equal to log to the base 10 P0 upon P. If you'll observe the relationship over here, P0 divided by P is 1 by T. So, if you want to convert that into percentage T, it will be log is equal to log to the base 10 100 divided by percent T. Now, why it is 100 divided by percent T? You can observe this equation. Let me quickly if percent T is equal to 100 multiplied by T, then 1 by T will be equal to 100 divided by percent T. So this value has been substituted in place of 1 by T. Now you know the formula for, say, log of A divided by B. It becomes log A minus log B. So similarly, it will become log 100 to the base 10 minus log of percent T to the base 10. But log of 100 to the base 10 is 2. So absorbance is equal to 2 minus log of percent T to the base 10. Now, if this is the relationship which is established, what may be, please think about it, what may be the maximum value of absorbance? Okay, let us go logically to answer this question. No, Shweta. Shweta, think what may be the maximum transmittance possible? Okay, percent transmittance, maximum can be 100% and minimum can be 0. So the absorbance value may range from 0 to 2, and transmittance value will range from 0 to 100. This scale over here is plotted using this formula. Okay, let's move on. Now, the reason behind why we observe the absorbance in UV range. So that absorbance of UV radiation by the molecule takes place because of the transitions within the molecules. Now, when we talk about molecules, which are types of electrons present in the molecule, there are three types of electron: sigma electron, pi electrons, and non-bonding electrons. Where are sigma electrons present? Obviously, they are present in sigma bonds. Where are pi electrons present? Obviously, they are present in pi bonds. Now, what about non-bonding electrons? Non-bonding electrons are present on heteroatoms present within the molecules like nitrogen, oxygen, sulfur, all the halogens. Okay, let me ask you a question. How many non-bonding electrons are present on chlorine? How many non-bonding electrons are present on chlorine? Shubham is saying 4. Okay, any other answer? Okay, Shubham Maurya is saying 1. Okay, this is one pair, this is second pair, and this is third pair. So total 6 non-bonding electrons are present in 3 n pairs. So this is one pair, this is second pair, and this is third pair. Okay, now can anybody tell me in water molecule how many non-bonding pairs oxygen carries? Excellent, Shweta. There are 2 pairs of non-bonding electrons and 4 non-bonding electrons present on oxygen. Very good. Okay, so these electrons which are present in sigma bond and in pi bond, they are called as bonding electrons, and one present in n orbital is called as non-bonding electron. There is something called as anti-bonding molecular orbitals. They are sigma star and pi star. Now, n electrons can jump in both of them when excited, when it acquires energy. It can jump into sigma star also, it can jump into pi star also. But pi electrons can jump into only in pi star, and sigma electrons can jump into only sigma star. Now, theoretically, sigma electrons may also jump into pi star, and pi electrons may also jump into sigma star. But these transitions are theoretical only, and they are not observed in practical. They are never observed. Okay, so only theoretical possible. So these two transitions are called as forbidden transitions. Which two? Sigma to pi star and pi to sigma star. Observe this animation for a while. Observe this animation. Okay, so these are 6 possible transitions: sigma to sigma star, pi to pi star, into sigma star, into pi star. Then these 4 transitions are observed in UV, visible. These 2 transitions are forbidden transitions: sigma to pi star and pi to sigma star. Now, which are chemicals, which are molecules that will show only sigma to sigma star transition? Obviously, the molecules in which all the bonds are saturated. Okay, all bonds present are sigma bonds. Those will show you sigma to sigma star transitions. Now, these transitions are associated with maximum energy. The reason being sigma orbital is most stable orbital, so it has got low energy. It is at far lesser energy state. To excite orbital which is at very low energy level, you will require more energy. More energy is associated with shorter wavelength. That's why these sigma orbitals, they absorb at 125 nanometer or around it. Next type of orbitals are pi orbitals. The transition is pi to pi star transition. Obviously, these transitions will be observed in compounds where pi bonds are present. Now, if you will understand the overlap of sigma orbitals and pi orbitals, you will also understand that pi orbitals are comparatively less stable as compared to sigma orbitals. So they are already in higher energy. To excite these higher energy electrons, you will require less amount of energy as compared to sigma orbitals. That's why these orbitals absorb at slightly longer wavelengths. So 170 to 205 nanometers is their absorption range. Next is N to pi star. Now, which all compounds, as per your guess, will show this N to sigma star transition? Obviously, you will require heteroatoms like nitrogen, oxygen, sulfur, and these heteroatoms should be connected to other atoms, say it may be carbon, via a sigma bond. There should be a sigma bond. Then only the n electrons which are present over here may jump into sigma star orbital. So you require a sigma bond and halogen or oxygen or sulfur or nitrogen. Okay. Now into sigma star transition is still associated with lesser amount of energy because n orbitals are not overlapping with any other orbital, so they are naturally present at slightly higher energy. So 150 to 250 nanometer you will observe these type of transitions. Now next is N to pi star transition. An electron from non-bonding orbital is promoted to anti-bonding pi orbital. Now, which all compounds will show these type of transitions in which you have n electrons and you have pi electrons or pi orbital? You need one heteroatom immediately present next to a pi bond, like in carbonyl group, in cyano group, nitroso group, and so on. Any group in which heteroatom is attached to carbon via pi bond, you will observe this type of transition. Okay. Now, this is the transition associated with least amount of energy. It is associated with least amount of energy, so you require longer wavelength in this transition. So at 300 nanometer also you will observe this. Now, sigma to pi star and pi to sigma star transitions are called as forbidden transitions. They are possible only theoretically. Okay. Thus, you will be able to understand this diagram. I will give you a minute to observe this diagram. Energy level for sigma bonding molecular orbital, energy level for pi bonding molecular orbital, energy level for n non-bonding molecular orbital. This is energy level for pi star anti-bonding molecular orbital. This is energy level for sigma star anti-bonding molecular orbital. Now looking at the diagram, can you type down transitions from least energy to highest energy? Everyone type down, observe the diagram and type down from least energy to highest energy. Most energy, okay, you want to go by that way, so write down transition first with most energy and go on decreasing the energy of transition. Come on, type down those all transitions. Okay, let us agree that sigma to sigma star is the highest one. What is immediately next to sigma star? Into pi star is least. Okay, into pi star is least. Okay, now we know what is least, we know what is most. Out of n to sigma star and pi to pi star, which one has least energy out of these two? Okay, we have established that this is associated with most energy and this is associated with least energy. Now compare these two. Pi to pi star is what? Less energy or more energy? Less energy. Very good. So n to sigma star is more energy. So overall, the energy transitions and their energy will be sigma to sigma star is most, then comes n to sigma star, then you have pi to pi star, and then you have n to pi star. I hope this is clear to you. Now let us study few more terms used in UV. Chromophore. It is the functional group. Okay, this definition is B-Pharm level definition. Functional group responsible for the color of the molecule. Now, M-Pharm level proper definition is functional groups containing multiple bonds capable of absorbing electromagnetic radiation about 200 nanometer due to n to pi star and pi to pi star transitions. Examples of chromophores are carbon double bond carbon, preferably present in conjugation, then carbon triple bond carbon, carbon double bond oxygen, carbon double bond nitrogen, carbon triple bond nitrogen, carbon double bond sulfur, and many other examples. Next is auxochrome. Auxano literally means to increase and chroma means color. So anything that increases color is literally called auxochrome, but that is very primitive definition. Proper definition is the functional group which when attached to chromophore increases the intensity of absorption. Okay. The functional group with non-bonding electrons. Functional group with non-bonding electron that does not absorb radiation by itself in UV region, but when attached to chromophore alters the wavelength and intensity of absorption. All halogens come in this range. You have OH group, SH group, NH2 group. Okay, so this is auxochrome. See, benzene, it is a chromophore. It may be attached to hydroxyl group or NH2 group. In both cases, you will observe that lambda max has shifted to longer wavelength. That means now the compound absorbs at lesser energy. Now, shifts in absorption. Okay, if lambda max of a compound shifts towards longer wavelength, it is called as red shift or bathochromic shift. Bathochromic shift. If we attach any auxochrome to the compound, bathochromic shift may be observed. Okay. Now, the other is blue shift. It is also called as hypsochromic shift. Hypsochromic shift is observed when auxochrome is removed or alteration in the structure is made such that lone pair or conjugation is lost. Similarly, hyperchromic shift. Generally, whatever changes you make to bring about bathochromic shift will also bring about hyperchromic shift, and whatever changes you bring in the compound to observe hypsochromic shift will also give you hypochromic shift, where the intensity of the absorption decreases. Okay, very good. Now let us see examples. First example is of bathochromic shift. You have paranitrophenol. You add alkaline medium. See, hydroxyl group over here is from phenol, so it is acidic. It is present like this. Let me draw it. See, this is OH. When hydrogen is lost to the solvent, this sigma bond will shift on oxygen. So oxygen over here carries one extra lone pair of electron. That extra lone pair of electron acts as auxochrome. Okay, and you can see the change in the wavelength towards longer wavelength. Then hypsochromic shift, this is an example. You have lone pair of electron present on amino group. When you add acid, that lone pair is abstracted by hydrogen. So lone pair is not available. You have removed the auxochrome character. So the wavelength has shifted towards left to shorter wavelength from 280 to 265. So it is hypsochromic shift. Hypochromic shift, you attach CH3 group and you will observe that absorbance per mole has increased. In hypochromic effect, you add CH3 and you will observe that the absorbance has decreased. Okay, solvent cutoff. For any solvent which is used in UV, it has got its own absorbance. Okay, so maximum wavelength till which the solvent is absorbing UV light is called as cutoff wavelength of that solvent. It is important value while you select the solvent for your analyte. These are different cutoff wavelengths of different solvents. I will give you one example. Chloroform over here will absorb UV light till 245 nanometers. So if you have any compound, any analyte whose lambda max is near to this, you cannot use chloroform. Next concept is isoabsorptive or isobastic point. If two compounds, they absorb equal quantity of intensity of light at particular wavelength, wave number or frequency, that particular point of wavelength, wave number or frequency is called as isobastic point or isoabsorptive point. Spectral bandwidth, this concept is related to particular filter. The amount of I should not say amount, the range of wavelength that is allows to pass through it is called as spectral bandwidth of that particular filter or monochromator. Okay, the lecture timing is over. Beer-Lambert's law we will study in the next lecture.